Hello class, this is CSE-5250, section 61, week 9, fall 2024. We're finally continuing with the long-awaited part 2 of our discussion on p-threads. I should note, we're only going to go as far as mutexes. Semaphores and condition variables are things that would have been taught back in CSE-4600. So, for our purposes, we're just going to go up the p-threads because, well, not only are... In a discussion on p-threads, we're only going to go as far as mutex locks because I thought, like, semaphores and condition variables would have been taught back in CSE-4600. And also, I really want to get the OpenMP because that's a bit more fun. And at least with OpenMP, you're not going to be restricted to using a Linux machine or Unix machine in general, because I will say right now, when we get to OpenMP, you have the option of doing this on a Windows machine. Okay, so we had left off with this. So these are all the files that we're going to make today. And for us to begin, we need to make a copy of our previous program where we had implemented our pi estimation program. So if you recall how this works, I'm gonna open a terminal here. I hope you can see this despite all the weird screen artifacts that are popping up. I don't know what this is, but I hope it's... I'll do my best to make sure it's not interfering too much. So, if I do /pi threads and press enter, I get a segmentation fault because I forgot to specify any parameters. I did not specify a thread count, I did not specify the number of terms. So I need to specify both for this to work. Ideally, what would be also good practice is if you have it so that you forget, if the user forgets to enter values, you would have some default values instead, say 100 terms and 10 threads. So maybe 10 threads might not be good in this case because, well, this is a virtual machine and I have it running with a limited amount of resources. So yeah. So for now, I'm just gonna say 100 terms and 10 threads. Okay, I forgot space. Let's try that again. Okay, so something's up. Okay, so something's going on here, and some factor, estimated value of pi should be 4 times the sum. Sum is a global variable. Maybe I need to recompile this. It's not working as I thought it would. Oh, there we go. It's reversed. Okay, so for this program, the first thing you enter after the name of the program, that is the number of threads. After that, it's the number of terms. So the more terms we have, the better of an approximation of pi that we get. It's just that when we ran this program, we had a bug where every time you ran the program, the sum would change each time. That's not good. So we're gonna address that today. So basically what's going on is this. We have a race condition going on. Basically we have, in a race condition, you have 2 or more threads whose results depend on the order in which they execute stuff. Here, we have a race condition because our threads are trying to access a shared variable. Basically what's going on is they're updating values, but we need to make sure that only one thread is updating that value at a time. In our Pi program, we have a race condition that's resulting in some of our terms and our summation being lost. So that's not good. It means every time we run the program, the value of pi is going to change. That's not good. And this is one of those things that you have to debug when it comes to parallel programming. How do you debug a race condition? So how do you fix it? Well, really all we gotta do is make sure that really the one key thing you need to know with fixing a race condition is to make sure that, in our case, one thread at a time can add to the global sum. We define what is called a critical section. That is an area of code in which a critical section is an area of code in which a thread is accessing some shared something, a shared variable in our case. So all we gotta do is add some mechanism that will make sure that whenever a thread accesses that shared variable, no other thread is allowed to do the same. And we're gonna do a simple implementation of this using what's called a busy wait. And if you're cringing at the idea of a busy wait right now, I'll explain in a little bit a much better solution. But for now, we're gonna implement a busy wait and deal with the consequences of that. So really all we gotta do is add another global variable called flag. This is a global variable that we are gonna add to our Pi estimation program, and in the main function, we're just gonna initially set that flag variable to 0. In the thread sum function, what we're gonna do is add two more things to our for loop. So now we need to define our critical section. Our critical section is whatever part of the code is accessing or doing something with a global variable. So our sum is a global variable. We're doing something to it. That is our critical section. So right before that critical section, we need to add code that's going to lock out a thread from accessing that critical section. So before we enter the critical section, here's what we do. We execute this while loop. Basically, when the main function set this flag variable to 0, basically it says, thread 0, you go first. If this code is being executed by, for example, thread 1, it's going to get stuck in this while loop because flag does not equal my rank. If this is thread 1, then my rank is 1. It means this while loop is going to be, well, there's nothing in this while loop, but what there is a condition being checked, like every iteration of the while loop. Basically, if this is thread 1 and thread 0 was allowed to go first, thread 1 is going to repeatedly check the flag and see whether it's not equal to my rank. It's gonna check that over and over and over and over and over again. And now, thread 1 is caught in an infinite loop. But not for long. Meanwhile, in thread 0, it's going to check the flag against my rank. And they're not equal to, but they're not unequal to one another. They're not equal to one another. That means they are equal to one another, which means this condition here evaluates to false, which means we immediately break out of the while loop. So now thread 0 is allowed to execute its critical section. Here's the next bit. After that, we have thread 0 increment the flag variable that tells thread 1, it's your turn to run. However, we need to do one extra step, and that is we need to perform a modulo operation. So when, and I'll show you why that is later in a little bit. When thread 0 incremented the flag variable, thread 1 was in this infinite loop of checking the flag over and over and over again, when that flag variable changes, that breaks thread 1 out of its loop, and now it can execute the code for adding a term to the critical section, within the critical section. After that, thread 1 is going to increment the flag by 1, and now it's thread 2's turn to run. So if we have a thread 2, it's going to continue on. Thread 2 was in its own busy wait. It was waiting for its turn to run. Now it's its turn to run, and then thread 3. And it's going to keep going and going and going until we get to the last thread. Let's call it thread N. It's going to increment the flag by 1, but this is where we need to do the modulus operation. So if we reach the last thread, we need to do a modulus operation. We need to do flag equals flag modulus thread count. That brings the flag back to 0. So an even easier example would be if we were running 2 threads. So this program would be alternating between 2 threads. It's thread 0's turn to run. Thread 1 is caught in a busy wait. Thread 0 finishes. It says to the next thread, it's your turn to run. Thread 1 runs, and then it increments the flag by 1. But since it's the last thread, it's going to increment by 1, but then it's gonna whip it back to 0. So it says, it's thread 0's turn to run now. So this is what our busy wait is doing. And all the slides basically say what I just said. So let's implement this and see what the consequences are. What I'm gonna do is cheat a little bit, and I'm just gonna copy this and create a new folder. pthreads busy. I'm gonna paste our. This is the code that you would have hopefully written in the previous assignment, because now we're gonna build on it in here. So the rules of implementing our busy wait require that we have a flag variable. So I'm going to add that flag variable now. Int flag, and I'm not going to set it to anything, but I will say shared variable to control access to some. And now, somewhere in the main function, I'm going to say set flag to 0, flag equals 0. Okay, so that is done. We now have the flag set in our main function. But now we have to go to our thread function, and now we have to define our critical section. It's right here. Because sum is a global variable, anytime we access that, that is our critical section. Because a critical section is where a program is executing code that accesses some shared something. In this case, it's a shared variable. So here's our critical section. I'm just going to add a comment. Now I need to add this. Before you enter the critical section, perform a busy wait. And here's the code for that. You do have the slides to refer to this, by the way. I'm just more or less copying off the slides. While flag does not equal my rank. And that's it. While left parenthesis flag does not equal my rank, right parenthesis semicolon. This is basically a while loop that does nothing except check that condition every time. Now, when we exit the critical section, we need to increment the flag variable by 1. So it looks like this. Flag plus plus, and then flag equals flag modulus thread count. Now there is a way to condense this into one line. It would basically be flag on the left hand side, and then on the right hand side, in parentheses, flag plus 1, and then modulus thread count. That works too. I'm just doing it as 2 lines for the sake of demonstration purposes. So basically, when we perform that incrementing the flag, we gotta do a modulus operation to make sure it rolls back to 0 if it was the last thread that incremented that flag. So that's it. I am now going to close this terminal, and then now I need to recompile this. So now we have our PyThreads program with the busy-wait. I need to recompile this program, however. So the command for this is gcc-g-wall-o, the name of the executable, the name of the source code file, and then -lp thread. So PyThreads, and then pythreads.c. Press enter. Hope that, okay, it compiled. That's good. Now, all I gotta do is run it again. /pythreads, press enter, and we get a sec fault. And that's because I didn't write in the arguments for that. So really we need to say, I want to run this with 100 terms, and let's start with 1 thread for now. Okay, I think I got it backwards again. So that should be 1 thread and then 100 terms. Okay, there we go. There we go. There we go. Yeah, so I guess if there's one thing to note, it's make sure that you enter your command line arguments in the right order. Because the first argument after the file name is the number of threads. The one after that is the number of terms. Let's just do our best to make sure we don't mix them up. Okay, we did it with 1 thread, and we got a value of pi. See? Let's try it with more threads. Let's try it with 2 threads. It worked. Let's try it with 4 threads. It worked. I'm gonna try 10 threads. It also worked. Okay, so let's clear that, and I want to do this with more terms. So I'm gonna do 1,000 terms with 1 thread. It works. Let's do it with 2 threads. It also works. Let's do it with 4 threads. It also works. Let's do it with 8 threads. Start to slow down. Okay, so now I'm gonna clear this, and now I'm gonna do this with an obscenely large number of threads, say 1 million. 1 million terms with 1 thread works just fine. If I double that to 2, we're gonna be here a while. So maybe I should just pause the recording and come back once it's finished. Yeah, so it's clearly taking way too long, and this is why we don't generally use busy waitings in this scenario. So in your assignment, I ask you to try to run the program with some number of threads and some number of terms. So now we're stuck here waiting for this program to finish running. So what you do in here for part 1 is you basically implement the busy wait and then run it a few times until you reach this scenario where you don't know where it's running at all. Basically, at this point, you just press Ctrl-C to forcibly force the program to close. So maybe let's try that with a much more reasonable number of terms, say 10,000. So I'm gonna do that with 1 thread and 10,000 terms. Do it again with 2 threads and 10,000 terms. It ran just fine. 4 also ran just fine. 8. And there we go. It's now slowing down because now we have so many threads busy waiting that it's slowing down the system. So maybe I need to adjust the instructions a little bit so it's at least, maybe for best results you gotta try it with 10,000 terms. Yeah, so at some point you're gonna reach this where the program, it looks like it's frozen, but it's doing something. But the problem is, it's not doing productive work. So that's the problem with the busy wait. So let's get back to our slides. We implemented our busy wait to enforce mutual exclusion. The problem is, it's too slow. It's freaking slow. So here's what's going on. The while loop that we added, that is a busy wait. The CPU repeatedly tests a variable until it changes. When a thread enters its critical section, it adds its value to the sum, then increments the flag to indicate it's time for the next thread to run. Here's the thing though. Each waiting thread, every waiting thread, is doing a busy wait. And the more threads we add, the worse it gets. Basically, every thread that isn't the thread that's allowed to enter the critical section is doing unproductive work. It works just fine with 1 thread because there's no other thread has to wait on. With 2 threads, it was still kind of fine until we went to 1 million terms to add, and then it just slowed down abysmally. So depending on which quantities you pick for your thread count and the number of terms, you might hit that slowdown immediately, or it may take some time to get to that slowdown. My point is this: once you add multiple threads, the program starts to slow down. At some point, the slowdown becomes so intolerable that you have to press Ctrl-C just to get the program to stop. This is called spin lock, by the way. So one thing we can also do is, when we run this program, we add the keyword time. What that does is, when we run the program, it gives us the runtime. So all we really need to know, all we really need to care about is the real time here. So when this program ran, it ran in, 1 millisecond? When we run it with 2 threads, it becomes abysmally slow. So let's go back to 1 thread and 1,000 terms. That took 1 millisecond. If we do it with 2, it also took 2. It also took 1 millisecond. If we did it with 4 threads, it also did the same. I'll do it with 10, and that's where we got our slowdown. That took 7 seconds. So basically what's going on is, the more threads we add, the longer it takes for the program to run. So yeah, when we parallelize programs with the intent of making them run faster, this is one of the pitfalls with You might not get a speed up. In worst cases, you might get a slowdown. However, in this case, the pitfall was trying to use a busy waiting in the first place. The reason why I have you do a busy waiting is to basically show you how bad it is. There are some scenarios in which it is okay to have a busy waiting if the wait is short. This is done with some handshake protocols, for example. But in the case of our pi estimation program, this is unacceptable. We need something else. That something else is going to be what's called a mutex. A mutex, short for mutual exclusion, it's a special variable that with two special functions. It does the same thing as a busy wait, except we don't have threads doing unproductive work. In operating systems, we assume that if a thread is unable to execute its critical section, it goes to sleep. When another thread that was executing its critical section leaves, it wakes up whatever thread was waiting for its turn on the critical section. pthreads has a data type for mutual exclusion, mutex. It's called pthread mutex t. We need a few more functions for this as well. We initialize a mutex using pthread mutex init. We pass in the address to mutex for the first argument, and for the second argument, we're not really going to do anything with that, so we're just going to pass in null. When we're done with the mutex, we call pthread mutex destroy, and all you got to do here is pass in the mutex address. When a thread wishes to enter its critical section, it must first acquire a lock by calling pthread mutex lock. We pass in the mutex address here as well. When a thread leaves its critical section, it calls pthread mutex unlock. And once again, we pass in the address to the mutex. Oftentimes, when we talk about mutexes, we talk about them being used as locks. So this is a physical analogy for like actual physical locks. We say a thread acquires a lock. This locks out any other thread from executing their critical sections. Once that thread leaves its critical section, we say a thread then releases or unlocks the lock. That signals to other threads that it signals to other threads that the critical section is now available to be executed by another thread. Though now we have to determine which thread is going to come next. It's for our purposes, we're gonna say if there are multiple threads waiting to execute their critical section, for our purposes, we're gonna say it's the next thread is gonna be random. And this randomness has some problems in some cases. With a busy waiting, with our busy waiting that we implemented earlier, because we increment the flag, we have a cyclical nature in which threads are executing. So it's always going to be the next thread in order, and then it loops back to 0 when it reaches the last thread. So with a busy waiting, the order in which threads executes their code is cyclical. With a mutex, the order in which threads execute their code may change each time the program runs. This adds randomness that we might not want with our program. But in our case, it's actually okay because addition is commutative. It doesn't matter the order in which we add terms. Basically, this randomness comes from the CPU scheduler. The CPU scheduler decides which thread to run next, so it's not guaranteed that the order in which threads execute will be the order specified by the rank. So it's not rank 0, it's not rank 0 and then rank 1 and then rank 2 and so on. It could be some random order altogether. The point is this. With our pi estimation program, this is a non-issue because addition is commutative. Basically, eventually, every thread will acquire the lock. So now we get to the fun part where we bug fix our own program. So what I'm going to do is I'm going to copy that. I'm going to call this pthreads mutex. Now we get to do the fun part of bug fixing our program. So now, instead of a flag, we now have pthread mutex t. So now we have our mutex. Instead of saying something like flag equals 0, we replace that with pthread mutex init. We pass in the address of the mutex, and we pass in null after that. towards the end of the program, so right around here where we deallocate memory for our thread handles, we destroy the lock because we're done with it. At this point in the program, we're done with the mutex, we can destroy it. So let me just grab the slide for that. The code to destroy the lock is pthread mutex destroy, and we pass in the address of our lock. I'm gonna use the term lock and mutex interchangeably here. So when I say lock when I mean mutex, I really mean mutex. But really it's useful to think of this mutex as being a lock. Because that's the common lingo for talking about mutual exclusion thingies here. Okay, so now we have our lock. Now we need to have our threads actually use the lock. So before entering the critical section, acquire the lock. Execute the critical section, and then when you exit the critical section, release the lock. So the use of a lock is pretty simple. All we gotta do is pthread mutex lock, pass in the address of mutex, and then I'll just cheat here, copy that line of code, paste it here, and replace lock with unlock. And that's it. That should, hopefully, fix all our problems with having a busy wait. But there's only one way to know for sure. And for that we have to compile the program. Let's recompile the program again. Here we are. So now it was pythreads, now it's pythreads mutex. So all we gotta do is change the file names, press enter, there we go, /pythreads mutex, press enter, and we get a segmentation fault because I didn't specify the number of threads or the number of terms. Let's fix that. Pythreads mutex, I'm gonna do 1 thread and 100 terms. And now we have an estimated value of pi being 3.13, that's not right. So let's do it with more terms. And now we get 1.140593, that's not quite right either. Let's do it 10,000 terms, it's getting a little better. Let's do even more terms than that. 141583. Let's stop it here, because I do want to do a test. It is this. Let's do it with 2 threads. And repeat it several times to confirm whether it's the right result each time. Okay, so if we look here, the estimated value of pi for 100,000 terms in 1 thread is 3.141583, and with 2 threads, it's about the same. Let's do it with 4 threads to make absolutely sure that it's not changing. Let's do even more threads, like 8 threads. And there we go. Now we know for sure, or at least with this small sample size, we know for sure that when our program is adding terms for the value of pi, it isn't skipping terms because of race conditions. So it works! Let's do another experiment. Now that we know that the program is working this time, let's do some runtime experiments. I'm gonna add the time command back here. So let's do 1 thread at a very large, with a very large number of terms. Let's do 100 million. That took about 2 seconds. Let's do 2 threads. The reason why I did it at 100 million is because it's gonna be divisible by several consecutive powers of 2. So I can do 1, 2, 4, 8, and 16 for testing purposes here. Okay, so actually it'd be really smart if I just kept all of these within here. So 1 thread at 100 million terms. The program ran for 2 seconds. With 2 threads, it ran for a bit longer. That's a little concerning. With 4 threads, it also ran for 6 seconds. And with 8 threads, we created this program with the intent that we would speed it up by parallelizing it. How come it's not getting any faster? In fact, it's slowing down the moment we add more threads. Well, it's because we did something a little bit dumb, and it's a little bit insidious as well. It's where we placed our critical section. So basically, we are doing access to a critical section every time we add a term. But what if we didn't have to do that? What if we could, instead of adding all the terms to, instead of each thread adding its terms to the sum for every for loop iteration it has to do, it adds them to its own local sum and then adds that to the global sum after the for loop. So instead of accessing the critical section for every iteration of the for loop, we access the critical section once per thread. So here's how we conceptualize that. So we're now addressing the issues of the fact that now we don't have any speed up at all. We made this with the intent of getting speed ups. We don't have speed ups. What's up with that? Well, now we're going to try to fix it. So basically, we're not dealing with an infinite sum. We're just taking an infinite sum and truncating it at some point, and now we have a finite sum. What we're doing is we're taking this finite sum and we're breaking it up into several smaller sums. Yo dog, I heard you like summations, so I put summations in your summations. So with that idea, and because addition is commutative and associative, this has no impact on the sum. So now, each grouping of terms here, that is a task delegated to one of our threads. So in this example where we have 6 threads, thread 0 is delegated the task of summing this first row of terms, and we call that S0. Thread 1 adds the next row of terms, and we call that S1. Thread 2 calculates S2, thread 3, thread 4, thread 5, and so on. It's at the end that we add these summations. So we have a summation of summations that we get our value of pi. Though, I should also mention that we don't get a value of pi when we add these sums together. We only get 1/4 of that, so now we have to multiply by 4 to get the actual value of pi. This means of estimating the number of pi, the value of pi, requires that you have to multiply it by 4. So that's really the last step we have to do. But really, this is really the part where we multiply it by 4 is the easy part. So now, with this in mind, what we're gonna do is have it so that each thread doesn't add terms to the global sum right away. It adds them to its own local sum, and then it adds the local sum to the global sum after. So, let's do that. I'm going to close this for now, and I'm gonna copy and paste this program again. I'm gonna call it PyThreads Mutex version 2. There we go. So now we open that, and now we get to tweak this thread function. Everything we need to do here is not going to be affecting anything else here. We're only gonna change the thread function itself. So let's fix that now. Right before our for loop, we're gonna add another local variable, double my sum equals 0. So this is gonna be our local sum. We're gonna take out this code and put it outside here. And we're gonna take this code and put it outside here. We're gonna do stuff with this later. I'm just putting it outside for now so I can make room for what I'm gonna do next. So, this is not a critical section anymore, because instead of adding to the global sum, we add to the local sum, my sum. So this is not a critical section anymore. Now, we're basically doing this. So we sum all of the thread's terms into one local sum, and then we add that local sum to the global sum. When we add that to the global sum, that is our new critical section. So now, before we enter the critical section, we gotta acquire the lock. And then after we leave the critical section, we gotta release that lock. So that's why I didn't delete these lines of code. I just moved them out of the way. So now, we have a new critical section. Add the thread's local sum to the global sum. So now, sum plus equals my sum. So basically now, instead of having one critical section access for every iteration of the for loop, we now have one access here. Save that, and recompile the program. So this is PyThreads mutex v2. I gotta change the file names accordingly with this compile command. Press enter, it worked. /PyThreads mutex v2. Got a segmentation fault because we didn't enter the number of threads or terms just yet. Let's fix that. So I'm gonna do this with 1,000. Yep. Go big or go home. Let's go straight for the 100 million. 100 million terms and one thread. Maybe I went too big too soon. Okay, there's the problem. I think I screwed up the terms again. There we go. Okay, so now we can go big or go home. Okay, so this is 100 million. I'm gonna add 100 million terms to estimate the number of pi, and we have 3.141593. If I do this with 2, no. Let's fix that up. One term. 2 terms. 4 terms. 8 terms. 16 turns. However, we don't know whether it's actually speeding up. That's why we need to try this again with the time command. Clear. And redo this with the time command. Press enter. We got a real time of like a quarter second. Now let's try it again with 2 terms. And hey, the time went down. Now it's 0.135 milliseconds. That's like a quarter second. A little over a quarter second. Now let's do it again with 4. Okay. 1 thread with 100 million terms. That's about a quarter second. 2 threads with 100 million terms. That did it in about half the time. If we did this with 4 threads, now we have 0.082 seconds. So it's even faster now. Let's do it again with 8 threads. And slowing down even more. No, it's speeding up even more. 16 threads, and we can keep going until we hit another wall. So now, check this out. Our program is speeding up now, the more threads we add. However, it's going to reach a point where the system just doesn't have any CPUs left to dole out to all of these threads. So at some point, we're gonna reach a wall, and that wall is the hardware itself. So basically, when we added this extra code, we rewrote it so that instead of the critical section being inside the for loop, it's outside the for loop. And now we have a speed up. We did it. We have a speed up in our program. The more threads we have, the more threads the program uses, the faster the program runs, up to a point. At some point, there will be more threads than there are available CPU cores. At that point, the program won't be running any faster anymore. In fact, it might start to slow down. So now, there's just one more loose thread here. And it is this. Let's run our program once more. And I'm going to demonstrate it with a smaller number of threads and a smaller number of turns. And I'm going to do this to demonstrate one more bug that this program has. I'm going to do this with 1 thread and 100 turns. It estimated the value of pi to be 3.131, whatever, and it's not correct. But we should know that if we do it with 2 threads, then we'll get the correct incorrect answer again. 3.13153. If I do it with 4 terms, I should also get the correct incorrect answer again. 3.13153. Here's the problem though. We coded this so that the number of terms is divisible by the number of threads. What happens if we didn't do that? Now we get an incorrect answer. 2 wrongs didn't make a right here. So we got the wrong answer of 3.13153. We were supposed to get the same incorrect answer of 3.13153. Now we got 3.151693. What? Basically, what's going on is this. For this, let's go in here and add a little bit of debugging code. It's this line of code here. So basically, let's add this line of code. And say printf thread %ld is adding %ld terms %ld to %ld dot \n, and then I'm gonna say my rank, my last I minus my first I, and then my first I, my last I. So basically, it's going to say thread number is adding some number of terms defined by the range defined by my last I minus my first I, and it's going to add the terms from my first I to my last I. This line of code, we're adding it for debugging purposes so we can see how many terms each thread is adding. So I need to recompile this program once again. So this is pthreads version 2, press enter, and I have another error here. I think I forgot to, okay, that error was, it's not %LD, it should be %LLD. There we go. Fix that up. Clear. Try again. Okay, so now let's rerun this program. Pthreads, pthreads version 2, press enter. Hold on. No, it's just file or directory. Ah, I misspelled it. It's by fault because we didn't specify anything. Let's do that again. Pthreads, pthreads version 2 with 100 threads, no, 100 terms and 1 thread. I did it backwards again. It should be 1 thread and 100 terms. So thread 0 is adding all 100 terms. If we have 2 threads, then it's divided between the 2 threads. So one thread is doing 50 terms, the other thread is doing another 50 terms. I accidentally put a typo here, but we're gonna roll with it anyway. That really should say terms plural, or maybe such that the S is in parentheses. Let's hold on. Let's reopen the terminal. I think it broke. Okay, so let's recap. With one thread was adding all 100 terms. With 2 threads are adding 50 terms each. With 3 threads, each term is adding 33 terms each. But 33 plus 33 plus 33 is 99. Where'd the 100th term go? It got lost. It went missing. And it only gets worse the more terms we try to add. So if I try to do it with 7, check this out. 14 to 28, and then 0 to 14, and then 42 to 56, and so on and so forth. And then we get to thread 6 adding terms 84 to 98. There's a missing term. So let's go back to the slides and try to tease what's going on here. So imagine back at our example with this grid of terms here. Instead of it being a 6x6 grid of terms, it was a 6x6 grid, but with a few terms in an extra row. What's happening is, if in this example we had 6 threads and 36 terms, if instead we had 38 terms, it means we have an extra 7th row that's not complete. That means whatever terms are in this last row here get missing. So last? No, this is last. We need to get these last terms, because if we don't, we're gonna make an oops here and forget to add them. So there are actually 2 ways to fix this, and one is rather simple and the other one is, in my opinion, a lot more elegant. So the first solution is this. Because we had observed that the last thread is missing some terms. Let's look here. We observed that the last thread was missing some terms. Thread 0 should be adding, in here, threads, with the 1 thread case, thread 0 was adding all 100 terms from 0 to 100. With 3 threads, it was divided 3 ways, but we had a remainder of 1. All I gotta do is add that extra term to one of these threads. What I'm gonna say is this. Check this out. Thread 2 is adding 33 terms from 66 to 99. And that's with the 3 thread case. With the 7 thread case, thread 6 is adding terms. It's adding 14 terms from 84 to 98, and it skipped a few. Here is our simple fix. All we gotta do is, if this is the last thread, it's going to add the last few missing terms. So it would be as though we went back to our example here. It would be as though, when we did this example, we did this row by row. At the very last row, it's going to expand a little bit to capture these extra terms here. And that is the fix. Or at least that's one of two possible fixes. There is another fix that's... Okay, let's look at the first fix. Basically, we get the last thread to add those missing terms. And the easiest way to do this is to add an extra if statement. If this is the last thread, have my last I be n instead, not my first I plus my n. Because if you have my first I plus my n, it might be less. If this is the last thread, then my last I might be less than n. If that is the case, then we need to make sure that my last I is n. That way we don't have missing terms. So this is the easiest possible fix. So let's try that right now. Let's go back here and create PyThreads Mutex version 3. Open that, and let's go back to our code here. We're gonna leave that debugging code for now. What I'm gonna do is this. If, okay, so the code is in the slides as well. So if my rank plus 1 equals thread count, if my rank plus 1 equals thread count, then my last I equals n. And there we go, we fixed it. Or at least that's the hope. Let's recompile the program once more. Clear. So this is now version 3. Press enter. PyThreads Mutex version 3. Press enter, and we get a segmentation fault. And that's because I didn't write the number of threads or the number of terms. I'm gonna do this with 1 thread and 100 terms. Thread 0 is adding 100 terms. If I do this with 2 threads, then 2 threads are adding 50 terms each. If I did this with 3 threads, I'm sure I fixed it. Oh, okay. I fixed it, but incorrectly. So let me just redo that and have the, if this is the last thread, have my last I be n. It was basically printing out debugging information before I applied the fix. So let's try it again. Clear. Let's recompile the program and try it again with 1 thread. Thread 0 is adding 100 terms. With 2 threads, 2 threads are adding 50 terms each. With 3 threads, 3 threads are adding 33 terms each, except for the last one, which is actually adding 34. That's because we had it add those extra terms that would have otherwise gone missing. If we did this with 7 threads, basically now we have every thread adding 14 terms except for the last one. That last one is actually adding 16 terms. So there is something called load balancing, and well, this wouldn't be balanced, but okay. So the idea of load balancing is basically what it says on the in the phrase itself. We balance. We have the work distributed among all our threads, so it is equal, or at least as equal as possible. With a scenario like this, it's only like one or two extra terms that we're adding. It doesn't really hurt the program this much in this case, and even more so if we are adding even more terms than like 100. So in this case, we don't really have to worry about load balancing. At least not yet, anyway. But my point is this. We fixed it. Now the program will work with any number of threads we want it to. So now, not only will the program work and get a speed up the more threads we have, we now have it so it can work with any number of threads. And that means we've done it. We have our first successfully working parallel program. We did it! Pat yourself on the back. Okay, that's actually just one way of fixing it. I want to show you the other way. And in my opinion, this is the more elegant way of having parallelized for loops. I'm going to show it to you. So now I'm going to make a version 3 copy. I'm going to call it version 3B. Open that. And this is the implementation I personally like more than using this my first I, my last I kind of stuff. And it is this. We rewrite the for loop altogether, so we don't even need a first I and last I or any of that. It means this debugging code will no longer work. So here it is. It also means this code here isn't really going to work either. So now we have to take that out for now, and I'm just going to put it inside the for loop. You'll see why. So double my sum equals 0. So it's still going to calculate its own local sum. But now, instead of starting at my first I, because we don't have a first I anymore, we're going to have it start at my rank. Instead of stopping at my last I, we're going to have it stop at n. And instead of I++, we're going to say I plus equals thread count. What this does is this. I like to talk about it as threads leapfrogging over one another. Remember when we had this summation here where we were doing it by the rows? I like to think of it as we're summing by the columns instead. So basically, in this example with 6 threads, instead of adding 6 rows worth of terms, with the last row adding like extra terms, it would be adding 6 columns. So it's like this. Thread 0 is tasked with finding the sum of its column. It starts at the 0th term, which is 1 here, and it goes up by 6 to add the next term after that, and then the next term after that is 6 terms. It goes up by 6 each time to add the next term, and then it goes up by 6 the next time to add the next term, and so on. Similarly with thread 1 computing S1, it adds the first term defined by not 0. It doesn't start at 0. It starts at a location defined by its thread ID. It's defined by its rank. So we say that's thread 0 starts at term 0, and that goes up by 6 each time to add the next term after that. Thread 1 starts at term 1, and it goes up by 6 each time to add the next terms after that. And so on. So now we need to do one other fix here. Because it's possible that the terms may alternate between even and odd, we need to add some extra code here to make sure that if this was an even term or an odd term, by even and odd I mean, by even and odd I'm kind of overloading it. So when I see even or odd, I mean, what is this value of I? Is it even or odd? Because we need to know that information, so we add or subtract the appropriate value. So basically, instead of my first I percent 2 equals 0, it's going to be, if I mod 2 equals 0, then it's going to be factor equals 1.0, else factor equals negative 1.0. This is to make sure we are adding or subtracting the correct term. So we're adding or subtracting the term. After that, we sum the thread's terms and add them to the local sum. And then we add those sums to the global sum. Save that. No. Now save that. So now I need to recompile this program once more. This is Mutex version 3B. Press enter, recompile the program. And finally, I'm going to do this with one thread and 100 terms. 3.131593. We're supposed to, now we know what incorrect answer we're supposed to get. If I do this with two threads, I get the same thing. If I do this with 3, I now get the same thing. If I did it with the 7, now we get the correct, incorrect answer each time. And but remember, it only becomes more correct. Only becomes correct if we add a lot of terms. Okay, now we get a much better estimation for the number of pi, but we don't have that nonsense where we have terms being lost because the number of terms to add wasn't divisible by the number of threads we had. So now it's fixed in one of two ways. So now when it comes to your next assignment, basically you're following along with the steps outlined in this video. So you're going to try out the busy way. You're gonna try out the mutex lock, and then you're gonna optimize your program, and then you're gonna bug fix your program so it works with any number of threads. And basically your deliverables are, you're gonna be including the source code and all the screenshots of your program running with all these different tests. So maybe you shouldn't try this 1,000 terms. Basically try it with a number of terms that is large enough that it would give you a noticeable slowdown. And that's it. This is your next assignment. With that, I'm probably gonna have it so that it is due within like 1.5 weeks from now. So just enough time for you to try and test out everything. After that, we're gonna move on to OpenMP because, in my opinion, OpenMP is a lot more fun. Okay, with that, that's the end of the video. Hope you have a good day. Try this out. If you have any questions, definitely shoot me an email. And we're gonna move on to the next chapter, OpenMP. That is chapter 5. Have a good one, and I'll see you next video.